Our third example of a single circuit element in which we'll try to find the impedance of is a circuit that has just a capacitor. So here is our capacitor, current, and voltage. And now when we look at the circuit equation for this circuit, we have that the voltage, and we've put plus Q and minus Q on the capacitor plates, is just Q over C. But again, in this instance, I is dq dt, because the way we've chosen our conventions, the capacitor is charging up. So we want to write things in terms of V and I, so we need to differentiate our equation here, and we get that dV dt equals dq dt 1 over c, so that's I over c. And now we do the same type of argument. First off, our voltage was given by V naught e to the I omega t. And when you differentiate that, you get I omega V naught e to the I omega t, 1 over c. Now we can just put in, we're not taking any derivatives on the current. So we have that. And now again, what we want is to cancel, to divide out by the time dependence e to the I omega t. And we get I omega naught V naught is I naught over c times e to the minus I phi. Now again, we want to make the two sides of these equations equal. So we'll find the phase by writing I, in this instance, as, let's write in our I, as e to the I pi over 2 times omega V naught equals I naught over c e to the minus I phi. And once again, in order for there to be equality, we've solved for the phase minus pi over 2, which is equal to delta in our impedance. Likewise, now we want to set up for the modulus of the impedance. So we want to solve for V naught over I naught. And when the two phase factors cancel, we have simply 1 over omega c. And so that's the modulus of the impedance. And so now we can write the impedance for a capacitor as modulus 1 over omega c times the phase, which is e to the I delta, and delta is minus I times pi over 2. Now remember, if I is equal to e to the I pi over 2, minus I is equal to e to the minus I pi over 2. And so what we have is minus I over omega c is the impedance for a pure capacitor. This is a pure imaginary number.